Hello, everyone, and welcome to our last part of our discussion about linear speed and angular speed. So, before we proceed, I would like to say something. So, as usual, after I finish discussing this subtopic, I'm going to have a practice, right? Which is that's the usual thing that I do. So after that, I'm going to have like let's just say an overall practice about angles and angle measures. Since we already tackled degrees and radians, length of the circular arc, then what's next? This is, what's that again? Yeah, linear speed and angular speed. So if we finish having a practice video about linear speed and angular speed, I'm going to have a overall practice about the topic of angle and angles measure. All right. So this is just to enhance our learning and mastery. Okay. So now let's proceed to our discussion. So let's have a recall. So recall that linear speed and angular speed are about getting the speed of an object in a circular motion. So the formula of the linear speed is v is equal to the arc length divided by time. And for angular speed is theta all over time. So W is equal to theta all over time. Now here, aside from knowing their formula, they're actually related to one another. Okay? Linear speed and angular speed are related. How though? How they are related? Well, if we're talking about graphical representation, we can say that they are related. Like for example, I'm just going to use this space for drawing. Right? We have this circle. So let's just say you start from here, then you end from here. All right. So you want to know the speed. Wait. Yeah, the speed from this. No, no, no. Let me try to rephrase. You want to know how fast does this object goes from here up to here, right? So it involves using an arc length. So that's it. So this is basically S. Now you see it also involves an angle. So let's just say we have this radius and another radius here. So it forms an angle. All right. So here, if on the red part, it's about how fast does this object reach from the from the initial up to the final position in terms of distance. Now, how about in terms of angular distance? So how fast does this angle form starting from here up to here? See? So in graphical representation, they are related. But uh, let's talk about formula. All right. Remember the arc length formula? Remember that, right? Now, try this one. I want you to divide this equation by t. All right. Or in here, multiply this equation by 1 all over t when t is time. So it would look like this one. All right. So multiply both sides by 1 all over t or divide both sides by t. So we have s all over t is equal to r, r, wait, let me just fix the r, which is, yeah, r all over t. There you go. So that's it. All right. So why did we do this one? Take a look though. We know that linear speed is v is equal to s all over t, and angular speed is theta all over t. So therefore, we can substitute s all over t as v. So we will have v. Then here on the right side, we can bring down r. Then we will have theta all over t. It's just the same, all right? It's just the same. And theta all over t is what? W. So we have this final derived formula. Wait, let me fix my W. It sucks. All right. This is our derived formula. So therefore, V is equal to R times theta. So this formula has both linear speed and angular speed. In other words, guys, in this formula, you can use this to find the linear speed if you have a given angular speed and a given radius. All right. Also, this equation indicates a relationship between the linear speed and angular speed. And what would that be? Linear speed is directly proportional to the angular speed. So what does it mean? It means that as the linear speed increases, the angular speed increases as well, and vice versa. So if the angular speed increases, the linear speed increases. And conversely, if this one decreases, then the linear speed also decreases. All right? So I hope you get what I mean here, because this is some of the important information about this formula. All right? So yeah, this is the new formula we're going to use. So let's try some examples. What will be the object's linear speed when the items, here we go again. Wait. Next time I would proofread this one sometimes, because object, item, they mean the same thing, but it could sometimes differ our interpretation, you know. So I'm just gonna write here objects. Forgive me. Anyways, so let's go. What will the object's linear speed be when the object's angular speed is 11 pi all over 4 radians per second, and a distance between the circle center and the item is 2.5 kilometers? Not item, it's the object. So with that, we can now substitute with this formula. So we have V is equal to R times W. So remember, W is the angular speed. So here we have the distance between the circle center and the object is 2.5. So meaning, if this is the center, okay, at this part here, the object, they're just 2.5 kilometers away from each other. So therefore, the radius is 2.5 kilometers times your W, which is the angular speed, 11 pi all over 4 radians per second. All right. So what would be the answer here? Okay. So for this case, we can use our calculator. 2.5 times 11 uh, pi all over 4. Yeah, 2.5 times 11 pi all over 4. So this is 21.60 approximately. 21.60 kilometers per second. So that is your answer. All right? 21.60 kilometers per second. So that means in 1 second, you can the object can reach, or the object reaches 21.6 or 21.60 kilometers. Okay? So before we proceed, I would like to ask you a question. This question is actually the question I asked you during the discussion we have about the length of the circular arc. All right. So you see kilometers per second. Why did I not include radian? I already similarly discussed this issue in the length of the circular arc. Okay. Why did I not include radians? Okay. Well, first reason, we are looking for the linear speed, right? And linear speed is about arc length all over time. So the arc length is not in radians, but rather it is in what? In length of the distance. So it could be meters, feet, inches, centimeters, and so on and so forth. Okay. And here's the second reason. The second reason is that radian is what? Radian is unitless. So therefore, we can what? We can disregard radians. Okay, we can disregard it. So therefore, we will have kilometers per second instead. But here's the question though. Okay, if it's unitless, then how about this one? All right, let's go back to our discussion last time. All right. which is this one, angular speed, right? If that's the case, why do we use radians for this case? If we know that radians is unitless, because I told you before that we use radians to represent a number that is in angle but not in degrees. So since here we're talking about angular distance and it should be in radians, so therefore if we want to know that the number used here is in angle but not in degrees, we're going to put radians. Okay? Okay? So if ever you're going to divide any number that is in radians by time, then it's about angular distance. Do not forget to include radian since it represents angle. All right? You get me? Because in this case, we're talking about angular speed, right? So we have angular distance and time. So we have to make sure that in here, the angle should be always present. And angle here is not in degrees, so rather it is in radian. So since it is an angle, so it's better to represent it as radian per second. Okay? So this shows the change in angular distance. All right? Just like for the linear speed, it's about change in distance, right? So meters per second, kilometers per second. But for this case, since we're talking about angles, so we need to convert it into radian and we will include radian here because angular speed is about change in angular distance. So we will have radians here instead. So radians per second. Because if we're going to remove radians, this answer this answer would be wrong because we're talking about angular speed here. So therefore, the unit should involve an angle unit that is in radian. Okay? So I hope you understand me. Then for this case, for the linear speed, here, for the linear speed, uh, for sorry, forgive me, I stuttered. Now for the linear speed, if you recall, it's about basically length divided by time, right? So distance traveled, but the distance traveled is in arc length. Okay, so it's s all over t. So therefore, since we're talking about linear speed and it's about the change in distance but not in angle, so we will disregard radian. All right. So therefore, you have kilometers per second. I hope you understand me. And if you think I speak that fast, I suggest you should watch it again. That explanation that I made. Sorry guys, because I have to finish these examples. All right. So what do you call this one? Bottom line, if it's a linear speed, it should be length and distance all over time. So meters per second and so on and so forth. So with this, we can just disregard radian because we're looking for the linear speed. And linear speed, again, only consists of the change in distance. So it could be meters, kilometers, inches, so on and so forth. But if you're looking for the angular speed, it should be in radians. Do not forget to include radians if it's about finding an angular speed. Okay? I already sum it up for you guys. Linear speed, meters per second, inches per second, or minute, whatsoever. But for the angular speed, if you're looking for the angular speed, there shall be radians, just like this one. All right? So now let's proceed to the last example. Think about a car that moves clockwise till it reaches its destination. From start to finish, or to the finish, an angle of 275 degrees is produced. The car from the center is 10 meters long. When the car reaches its end, determine its linear speed. Now, let's take a look at this one very closely. All right? So, first and foremost, right, we're going to use the formula, which is V is equal to R times W. But here's the problem. What are the given? So first, we have a given angle of 275 degrees, right? Next, the car from the center, which is basically a radius because you're talking about the distance between the car and the center of the circular path is actually what? In 10 meters long. All right. By the way, I think I forgot to mention. I uh, but moves clockwise. Okay, okay. By the way, this is actually in ano, in circular motion. Okay, this is in circular motion, not in one-dimensional motion, or like imagine driving in a road that is not circular path. Okay, this is in circular motion. Okay, the scenario here is that we are traveling, or the car is traveling in a circular motion. Okay, so anyways, let's proceed. So that's the radius. Okay, we're good. But here's the question: we do not know our angular speed because we have a given angle here only. Oh yeah, by the way, I forgot to include that the the time reaches from the start up to end is actually 25 seconds. Forgive me, 25 seconds. All right. So the time it reaches from the start up to finish is 25 seconds. All right. Sorry, I forgot that to include in this slide. Okay. So yeah, going back, you have the radius, you have the time, you have the angle. But it's not enough to find the linear speed because you need the angular speed and the radius. What do we have here only is the radius, which is 10 meters. So how are you able to find the linear speed when we have other givens such as the angle and the time, 25 seconds? So you're going to find the angular speed first. So what's the formula of the angular speed? W is equal to theta all over t. So here, theta is 275 degrees and we have 25 seconds. But we need to convert this angle into what? In radians because it is in degrees. So we will multiply 275 degrees by pi all over 180 degrees radians. All right? Uh-huh. I'm not sure what would be their common denominator, or sorry, common factor of 275 and 180, but I do believe it's 5. So I think let's start with that. All right? So let's start with that. 275 and 180 degrees are both divisible by 5. So 275 degrees divided by 5 degrees is 5. 55, sorry, 55. Okay. Then 180 degrees divided by 5 degrees is 36 degrees. 36 only. So yeah, I think that's it. I think this is already in simplified. 55 divided by 36. Yeah, this is already in simplified form. So simplified expression. So we have 55 times pi all over 36 radians. So the answer here would be 55 pi all over 36 radians. All right. So that would be the angle here. So we will have now 55 pi all over 36 radians divided by time, which is 25 seconds. All right. So now let me just put the answer here. If you're going to multiply this one, you simplify, I mean, you will have 55 pi all over 25, right? So 36 times 25. This is 900. Wow, that's long. 900. Oh, 900. Wait. Damn it. Okay. Anyways, 900 radians per second. Okay. So we can simplify this one because both of these number, 55 and 900 to be particular, are both divisible by 5. So 55 divided by 5 is 11, and 900 divided by 5 is 180. Oh, am I right? Yeah, 180. So your angular speed is 11 all over 180 radians per second. Now with that, we can now substitute this angular speed to this and multiply by our radius, which is 10 meters. So we will have now V is equal to 10 meters times 11 all over 180 radians per second. 10 and 180 are both divisible by 10. So 10 divided by 10 is 1. So we will have 1 meter. And 180 divided by 10 is just 18. So we have 1 times 1 all over 18 radians per second. All right, meters, by the way, this is meters. Okay, let me fix that. 1 meter. So the answer here is 11 all over 18 meters per second. Or let's approximate this answer. So 11 divided by 18 is 0.61 meters per second. All right, 0.61 meters per second. All right, and that's it. All right, that's how you find the linear speed with this formula. That is all, guys. So see you soon, guys, in having, sorry, what was that again? Yeah, so see you soon for the next video uh, about having a practice of what we learned so far about linear speed and angular speed. See you soon.